This video lecture is meant to cover the information found in Unit 15, Acids and Bases, and you should have a note packet that looks like this. Now you've already filled in these charts, or if you haven't, you should fill in these common acid names and common base names, which you can look them up in your textbook. Chapter 19, Section 1. You are responsible for knowing the names of these acids and bases and recognizing their chemical formulas. You also used your lab manual, experiment number 31. There's a lab called Properties of Acids and Bases. You should have read the background section and answered the questions, which just gives you a generalized background of acids and bases to get us started. And so you would have filled in both the first and the second page of this note packet. If you have any questions, make sure you see your teacher, or make sure you see me if you have any questions or concerns about any of these answers. We're going to continue on with objectives 3 and 4, which state that we will compare and contrast the acid-base theories of Arrhenius and Brønsted-Lowry, and we will identify conjugate acid-base pairs in equations. Molecular theories of how acids and bases work. Well, there's two main theories that you will be responsible for knowing, and Arrhenius' theory says that acids, when they are aqueous, when they're dissolved in water, will give off hydrogen ions as the only positive ion. So for example, if we had hydrochloric acid, when we make that aqueous, when we dissolve it in water, it will break apart, it will ionize, it will dissociate into the positive hydrogen ion, which will be aqueous, and the negative chloride ion also will be aqueous. So what this is saying is that the only positive ion that HCl breaks into is the hydrogen ion. Bases, when they are aqueous, will give off the hydroxide ion, which is OH with a -1 charge. It's called the hydroxide ion, but you should know that already, as the only negative ion. So bases will give off hydroxide as the only negative ion. So the example here, if we had sodium hydroxide and it were aqueous, meaning dissolved in water, it would dissociate, it would ionize and separate into the positive sodium ion, that would be aqueous, and the hydroxide ion, which would also be aqueous. The Brønsted-Lowry theory, similar in some ways, but the terminology is a little different. Brønsted-Lowry theory says that acids are proton donors. So let's think closely about this. If we use HCl as our example of an acid again, when we make it aqueous, it dissociates into a hydrogen aqueous ion and a chloride aqueous ion. So how is that any different? Well, it's really the terminology. The hydrogen ion is a proton because a hydrogen ion has in its nucleus 1 proton and 0 neutrons. Because it's a +1 ion, it's lost its one and only electron, so what is left in this ion is nothing more than a single proton. So really, the mechanism isn't any different. It's just referring to the positive hydrogen ion as a proton. Okay. So you might think, well, what difference does it make? You know, okay, call it a proton, call it a hydrogen ion. Well, what this definition allows us to do is to think about what bases do a little differently. And so if acids are proton donors, bases are considered to be proton acceptors, proton receivers. If someone's going to give away a proton, there's going to be someone else who takes the proton. So if we think about it this way, and I'm going to show this a little differently, a hydroxide ion, OH-, when it's aqueous, will get combined with that proton, that hydrogen ion. Right? So the hydroxide is the proton acceptor. this hydroxide is going to accept the proton. And you might guess what will happen when that hydroxide accepts the proton. You see 2 hydrogens and 1 oxygen. The charges cancel out, and what you end up with is water. All right, of course that would be liquid water. You can't have aqueous water. All right, well, I'm going to scroll down here to see the rest of this page. In reality, hydrogen ions, single protons, do not exist in aqueous solutions, or they're not found alone in aqueous solutions. Instead, they are found attached to water molecules, kind of like the protons are getting a piggyback ride. Okay, and so this is an artifact here. This has a positive sign on that hydrogen. All right, so that proton that we just said was floating around free in the water doesn't actually exist this way. It's getting a piggyback ride on that water molecule. And when that water molecule picks up an extra hydrogen ion, well, what do you have? You have H3O with a +1 charge. Well, this is an ion called the hydronium ion. You need to know that name, and you need to recognize that chemical formula. So let's think about how this works, right? If we were to look at this mechanism in an equation, I'm asking you here, it says to identify the Brønsted-Lowry acid and base in the following reaction. HC2H3O2, you know that as ethanoic acid. It is more commonly known as acetic acid, or the acid that is found in a vinegar solution. If you take that acetic acid and you combine it with some water, here's what will happen. The acetic acid is an acid because it's going to give away that hydrogen ion. That hydrogen ion is going to be picked up by this water molecule. So that right there classifies the HC2H3O2 as an acid because it's donating the proton, and the water is receiving that proton, so we call the water a base. Now this is kind of odd because water is typically thought of as a neutral substance, but it's acting as a base because it's receiving that proton. Now what you now have to think is, after this acetic acid gives away this hydrogen right here, what's left? Well, what's left is C2H3O2 with a -1 charge. All right? And then what's left of H2O after it accepts that proton? Well, it becomes H3O with a +1 charge. All right, so now what we have to think, well, you recognize right here, this is a two-way arrow. This is a reversible reaction. So let's look at the product side and try to figure out which one of these two substances, the hydronium ion, the H3O+, or the acetate ion, the C2H3O2, which one of those two things, if we look at the reaction in the reverse, which one of those two things is giving away its hydrogen? Well, you have to think like you're reading this sentence from right to left. The H3O is going to give away one of its hydrogens to the acetate ion. And how do you know that? Well, look, if you go to the left here, you'll see that H3O has to become H2O. So it's lost a hydrogen ion. So that classifies the H3O, the hydronium ion, as an acid. And the acetate ion has to be classified as a base because it took that proton. Okay, so that's what we are talking about when we say identify the Brønsted-Lowry acid and base. Okay, we have the acetic acid and the hydronium ion. This one and this one are the acids. And the water and the acetate ion are behaving as base Brønsted-Lowry bases. All right, but now we're going to shift the way we look at these acid-base pairs. You're going to have to identify who's the Brønsted-Lowry acid-bases in these equations. But then we're going to look at them a little bit differently. We're going to study what it means to be a conjugate acid-base pair. So we're moving on to part B of this notes section. Right? And this first sentence is kind of what we just talked about. Because all acid-base reactions are reversible, after an acid donates a proton, it is capable of accepting a proton, thus acting as a base. So let's look at this process similar to the acetic acid one we saw up above. We have hydrochloric acid and we have water. You might guess from those names that the hydrochloric acid is the acid, which means that the water is going to have to act as a base. Well, let's verify this. If you look at HCl on the left, if it's going to give away its hydrogen, who does that hydrogen have to go to? Well, that hydrogen has to be given to the other substance on the reactant side. Can we verify that by looking at the products? Well, when hydrogen gives away, or I'm sorry, when the HCl, when it gives away its hydrogen, what's left is chloride. When the water, H2O, receives that hydrogen, it becomes H3O plus 1. Okay. So therefore, let's look at this from the reverse side. What happens going from the products to the reactants? Well, the H3O is going to give up its one hydrogen to the chloride. The hydronium will then become water, H2O, and the chloride ion will accept the hydrogen from the hydronium to become HCl. So the hydronium will act as an acid, and the chloride will act as a base. But now what we're going to do is notice the acid on the left side and the base on the right side. HCl and chloride. This is what we call a conjugate acid-base pair. So I'm going to write that right here. HCl and Cl minus. The other conjugate pair is going to be the base on the left side of the equation and the acid on the other side of the equation. So I'm going to write down that those formulas are H2O and hydronium plus 1. So what do you notice about this first pair? HCl and Cl are related because one has, the only thing different about them is the hydrogen ion. Okay? The only thing different between a conjugate acid-base, a conjugate acid and its base is a hydrogen ion. We'll notice that over here as well. Water and hydronium, the only thing that makes them different is one hydrogen ion. The other thing that you will notice about a conjugate pair is that the conjugate acid and the conjugate base will always be on opposite sides of the equation. I'm going to write that in here. Will always be on opposite sides of the equation. All right, so now we're going to do a little more practice with identifying conjugate acids and bases. All right, and the first thing you have to do is you have to identify the Brønsted-Lowry acids and bases. So start by looking at the reactant side. And you'll notice what we have here is ammonium and hydroxide. And on the product side, you'll see ammonia and water. Okay, and so what you can see is that the ammonium here on the left side right here and NH3 are related because they are, the only thing different between those two is that there's one hydrogen atom difference. Okay, the other pair is going to be the hydroxide and the water. So we see that those are conjugate pairs, but now you have to decide which one's the acid and which one's the base. So if we look at the ammonium and the ammonia pair, okay, that pair right there, you can tell which one's the acid because it will have one more hydrogen than the other one. So in this case, the conjugate acid is the ammonium and the conjugate base is the ammonia. If we take a look at the other pair, hydroxide and water. The substance in this pair that acts as the acid will have an extra hydrogen. So in this case, the water is an acid and the hydroxide is the base. Okay. So let's go to take a look at number 2. What we see here is H3PO4. That's called phosphoric acid, reacting with water to produce the hydrogen phosphate ion and hydronium. Okay. What you'll notice, find the conjugate pairs just by recognizing the two substances on opposite sides of the equation that are related by, or the only thing different between them is one hydrogen. The first pair I will look at is water and hydronium ion. Whichever one of those two has an extra hydrogen is considered to be the acid, and the one that has one less hydrogen ion is the base. Let's look at the other set, H3PO4 and H2PO4. The only thing different is one hydrogen. The substance with the extra hydrogen will be the acid, and the other one will be the base. Number 3, HF, hydrofluoric acid, and water turns into hydronium and the fluoride ion. I recognize that HF and F are similar. I recognize that HF has an extra hydrogen compared to the fluoride, so HF is the conjugate acid, and its base, conjugate base, is the fluoride. The water and the hydronium are related by one hydrogen. The one with the extra hydrogen is the acid. The one with one less hydrogen is the base. All right, if we continue on, we'll see the same thing. Number 4, water and hydronium. Hydronium has the extra hydrogen. Water has one less. HI and iodine. The HI is the acid. The iodine, or the iodide ion, is the base. CH3COOH, this is a different way of writing ethanoic acid or acetic acid. On the right side, CH3COO. We see the one with the extra hydrogen is the acid, and the one without that hydrogen is the base. Water and hydronium. Hydronium's the acid. The water molecule is the base. One more, HSO4 is related to SO4 by one hydrogen. The HSO4 has the extra hydrogen. It's considered to be the acid. The sulfate ion then, therefore, is considered to be the base, the conjugate base. H2O and H3O, the hydronium with the extra hydrogen is the acid, and the water is the base. Okay, let's scroll down and take a look at this chart down here at the bottom. Whoop, too far. Okay, now we're going to look at this a little differently. If I tell you that NH3 is the conjugate acid, who is or what is its conjugate base? Okay, well, remember, an acid will always have one more hydrogen ion than the base. So let's take away one of those hydrogens and make it NH2. But if you're taking away a positive hydrogen ion and it was neutral to begin with, you're going to end up with an NH2 minus 1. All right, let's try that again. H2PO4 with a minus 1 charge. I'm telling you it's the acid, so one of those hydrogens is going to go away. What's left is HPO4. But you've lost a positive ion, so now the conjugate base will be a little bit more negative. And since the H2PO4 started at -1, HPO4 is going to go down to -2. HCO3 minus 1 charge. That's the acid. Its conjugate base will have lost one of the hydrogen ions. So what's left is CO3 minus 2. Water. If water is H2O and it's the conjugate acid, what's left after it gives away one of those hydrogens? Well, you might say HO, but if you really recognize that, we would rewrite that as, we wouldn't do that as HO. That's just not the standard way to do that. You rewrite it as OH. It was neutral. It's going to get more negative, so it goes down to -1. So you recognize the conjugate base is that hydroxide ion. HSO4 minus 1. Losing one hydrogen, what you're left with is SO4. It started out negative. We just got more negative to make it -2. All right, let's try going in the other direction. If NH3 is the conjugate base, what's the conjugate acid? Well, remember, the conjugate acid is going to have one more hydrogen. So let's add a hydrogen to this, NH4. But what we're really adding is a hydrogen cation, the +1 ion. So now the conjugate acid has to get more positive, so that becomes a +1. And you'll recognize that as the ammonium ion. H2PO4 -1. If that's the conjugate base, the conjugate acid is going to have one more hydrogen, so call it H3PO4, and it will become more positive. So instead of being -1, this now becomes neutral. HCO3 -1. The conjugate acid would be H2CO3, neutral. H2O is the conjugate base of H3O +1, the hydronium ion. HSO4 with a -1 becomes H2SO4, neutral. All right, looking at the remaining part of this chart. Hopefully you're able to do these on your own. Take a moment to pause, try them, and then come back and take a look at the answers. So if we're looking at the answers, H2S is the conjugate acid. It's going to lose a hydrogen to become HS -1. HBr will have the conjugate base of the bromide ion, Br -1. And HS -1 will become a conjugate base of S -2. The fluoride ion F -1 will have a conjugate acid of HF. CH3COO, the acetate ion, will become CH3COOH. The hydrogen is typically written on the end of that if that's how the formula is being written, and that will be neutral. NO2 -1 will become HNO2, neutral. All right, so you should be expected to be able to identify conjugate acid-base pairs both in an equation, like we did at the top of this page, but also if I just gave you a formula and told you it was the conjugate acid, or I asked you to find the conjugate base of that substance, I would also expect you to be able to do that. All right, this concludes this first video lecture on acids and bases, covering the objectives of number 3 and number 4 from your objective sheet. We'll see you in the classroom.